Okay. So the recording has started. Just to be sure, I'll just mute everybody else for now so that okay, so everybody is already muted. Okay, so let's start. Okay. So this course is on antennas and radiating systems, which is essentially the antenna theory course, which if you have done in your bachelor's or master's, so it's just the name. It's an antenna theory course. And something about me. So this is how I look. I won't be turning on my camera because my room is very shabby right now. My name is Anand Kumar. I'm a Prime Minister's Research Fellow at the Department of EC, the Indian Institute of Science, which is in Bangalore. I'm also a visiting research student. I'm also a visiting research student at the Tyndall National Institute, University College Cork, which is in Ireland. So I have done my bachelor's in electronics and communication engineering at the Indian Institute of Technology, ISM Dhanbad. I've got these two awards recently, so I'm very happy to share that I got the IEEE APS Society Fellowship and the MTT Society Fellowship. So I'm doing my PhD and I primarily work on space-time varying metamaterials. I use computational electromagnetics, specifically finite difference time domain method and non-reciprocal systems. So I've conducted courses on FDTD with the regular FDTD and the FDTD with telegrapher's equations, and they are available. The class recordings and slides are available on my course website and YouTube. So if you are interested in FDTD, maybe you can go through those lectures. So the lectures come with the MATLAB codes and all the steps. So and the simulation results and everything. So if you are interested, you can go through them. This course is I've also taken a course on microwave theory, just the passive parts, passive circuits, and this course is on antenna theory. So we already have had quite some issues with Teams now. So Teams is a problematic platform, but this is the only platform where I have access to conduct classes more than 60 minutes or so. Microsoft Teams is this is how the interface looks like. You're already familiar. If you have not seen, so this is how it looks like in a laptop or a desktop. Different version will be there on your mobile app. So there's a chat button over here, so you can write your questions, comments, and everything over there. So I can see, hello guys from Rohit Verma. Hi Rohit. Yeah, so you can see how the chat works. There is this people button over here, which lets me see if you have which gives the list of participants, and there's a raise hand button over here. So if you raise your hand, I'll be able to see a hand like this, and then I can ask you to unmute if you have a question. Um, so this is how the Teams window looks like. Over this area, waiting for others to join over here, you will be able to see the slides. So this is Teams. And let's start with why you should do this course or who is this course meant for. So this course is essentially for everybody in the electrical engineering or related areas. So if you're a bachelor student, the aspects of this course will cover your GATE exams or other related exams, IAS and stuff. And you might have a course on antenna theory in your program, or if you're just interested in antennas and radiating systems. If you're an MTech student in electrical engineering in my in microelectronics or similar areas, this could be part of your coursework. And if you're doing a specialization in this, if you're a PhD postdoc, you might just want to go through sit in the class, listen to it just to revise. Um, if you're from industry, this could help you go through the textbook without having to read them. So I'll be going. The slides are copied from one of the textbooks, and it's exactly line by line. I'll just be talking through the textbook. If you're interested in antennas and just want to revise, and if you plan for higher study, this is true for both bachelor's, masters. If you plan for higher studies in antennas, okay. Okay, somebody said that my screen is not visible. Can someone confirm if that is true?
Screen is visible. I'm able to see why this course.
Okay, you can see the why this course slide, right? Okay. So, Jitendra, if you can hear me, this I'm sharing the slides. Maybe you could leave the meeting and join back. That might solve the issue. Again, Teams is a problematic platform, but I can forced to use this. Uh, so, if you are having trouble, you can log in, log out. For the first few slides will be based on class logistics before we start. So that's all right. Um, Okay, so for industry folks, you could have these one of these reasons, and what you can expect from this course is basic understanding of basics. So I'll be showing you what is written in the textbook, and I'll talk about it. I'll give you an idea of what those equations are meant to be. I won't. This is a disclaimer that I won't be doing the math for you. You have to do it on your own. So if there's an equation, there's another equation below and the second equation follows one by doing math. I won't do it for you. If there is an integration, you have to do it yourself. So that's how you will have to learn. But I'll tell you what those two equations mean, and that's what this course is about. So will be running very fast with the course. This is a very short course covering syllabus, which is usually meant for 40 lectures or 30 lectures. We'll be doing that in 12. And also this meeting has been scheduled for 3 to 5:30, which is 2.5 hours duration. But the material will usually be around 1 hour, 1 hour, 15 minutes, and rest is meant for discussion, else we'll close early. Okay, so if you're preparing for GATE exams, this could be a revision for you. Do not rely on this course exactly for solving problems. This will give you an idea, but this will definitely help you. And if you have never not read any literature on antennas before, you will be able to follow them now after this course. So this is an idea of who this course is meant for and how it will affect you. This is the course outline, which was already shared in the course pamphlet, the flyer which went around. I posted it on LinkedIn and WhatsApp in some groups, and received actually quite a few registrations. Um, so we'll start with an introduction to this course. Then today we'll cover radiation fields of elemental dipoles, electric and magnetic dipoles, and then we'll look into these topics: antenna patterns and parameters, linear antenna arrays, receiving antennas, spreads and stuff. So we'll go through these. Maybe 8 and 9, not very much. We'll discuss briefly. So there's a hand there. Yes, Ashutosh.
Do we cover microstrip and patch antenna also? Microstrip antenna theory of that actually.
We'll see if
Related to that when you come to the simulation or something like that.
Okay, so good question. Whether there will be simulations or not? No, there will be no simulations. This is just a theory course. We might solve some problems or numericals, but no simulation, no CST, no HFSS, if that's what you're expecting. Regarding microstrip antennas, if we have time, we might discuss the physics behind it. But let's see. Once we are done with FIS, we'll see how many classes we reach there. If we have time, we'll do.
Okay, fine, fine. Okay, you have mentioned in six receiving antenna. So basically, the receiving antenna and transmitting antenna both works on the same principle, right? Now,
Yeah, it's the
so I
same
don't think
principle.
so.
Yes.
Okay, I don't
So
think why the receiving
it's
antenna you have to specify actually. Fine.
Oh, okay. So this is exactly, so I'll show you. This is exactly what the syllabus is in the course outline is from the textbook which I'm following. So I'm not changing words. It will remain the same. So if you have any doubts, you can refer to the textbook. So the textbook is DK Cheng. So yeah, here it is. So this is the textbook. I'm using this particular edition. The cover looks like this. It could also look different. So it's the chapter 11. So the course name comes from the chapter 11, and the course outline comes from all the topics which are inside. So I'll be strictly following this particular textbook. If you want to go in more details, a very good book which you might already know is Antenna Theory by C.A. Balanis, like the Bible of antenna theory. you can go through this book. These are there are other books which are also very good, but we'll stick to DK Chang for this course. All everything written on the slide, you'll find it in the textbook. Okay, so if you want the if you can find the PDF online, you can buy the book. It's pretty cheap, 500 600 something, which covers almost every topic for an RF engineer. I can also share the PDF if you want. Write it in the group if you need it. Okay. So how will we get the class slides, class recordings and stuff? So there's a course website which I'll post the link in WhatsApp after the end of this class. So this is actually I made a site on Google, and the link will lead you to this particular page. So this will how it looks. So I've hosted other courses as well. So slides for those are also available on the same same web page. If you click on this particular link, antennas and radiating systems, it will lead you to the link to the course of this particular course. So I have to update this, but the slides will come next to these bullets. So I'll write slide one or lecture one or something like that, and if you press the link, it will open a OneDrive link. So that's how you'll get the slides on the course website. It will be always there. And then again in the WhatsApp group, this is how the WhatsApp groups look like. I had pasted the Teams meeting link. There was some issue with that. I'll try to figure that out after this class. And inside this group, I'll paste these slides. I'll upload the PDF. Most likely PDF because PPT will be too large. With the PDF, and then the and the class recordings. I'll upload them on YouTube as an unlisted playlist. So you'll need the link to the to access the YouTube video. You cannot search it for duration of the course, but after the course, I might make them online. But for the duration of the course, the class recordings will be available on YouTube, but you need the link to access it. Yeah, you can't search it. So that's uh, about the file sharing. Now about the assignments, there will be I give some questions which could be from the assignments from the textbook or from the problem examples inside the course like in the chapter 11 of DK Cheng. I might also refer to other books. So the assignments are just meant for you to practice. I'll try to share the solutions. If something has to be discussed, we can do that in the class, but you have to message me or ask if you want that particular question to be discussed. Assignments will not be checked, so you need not return them. I encourage self-evaluation. So what you can do is try solving the questions and then refer to the textbook if you have solved it correctly. And yeah, again, if you have doubts, you can reach out to me. So I'll pause here. I'll take questions, and anything related to the class logistics or about this course. And also a question, is everyone on the WhatsApp group? If not, there's a QR over here, and I think I'll paste the WhatsApp group link again in the chat for this particular uh, meeting. Let me see. Okay, so I have pasted the WhatsApp chat link or the group link in the Teams meeting here if you have not joined the WhatsApp group. Uh, I guess there are no questions regarding the class logistics. So we'll start with the class. So I'm hoping everybody has done an electromagnetic theory class before this because we won't be going into electromagnetic theory. We'll just borrow equations and stuff from there, and then we'll use them. So in electromagnetic theory, we basically study the propagation characteristics of the plane waves, and source-free media. So we do not bother how the waves were generated. But in this course, we will focus on how the waves are generated, which are basically antennas. So the electromagnetic waves originate from sources, which could be time-varying charges and currents, and and these charges and currents have to be distributed in particular ways for the waves to generate. And antennas are the structures which are designed for radiating these fields. So if there is an oscillating charge or oscillating current, so you will need an antenna to help the wave propagate. So it might it might not propagate. There might be some propagation, but the antennas help these waves. They allow them to be launched into free space. So throughout this course, we'll learn about the antennas and how the fields are generated. And without an efficient antenna, the electromagnetic energy would be localized. So what means is if you have let me use pen. So if you have an oscillating charge, what will happen is the fields would radiate, but it would die down. But if the antennas are there, if it is an antenna, it would radiate properly. So that something like that, if to remember. So if you don't have an efficient antenna, the waves won't propagate to a longer distance, which is what we need. Now an antenna, they come in various shapes. It could be the simplest ones are the straight wire or conducting loop, or for if you have heard about horn antennas, it could be an aperture at the end of a waveguide, which is called horn antenna. Or it could be a complex array of wires, loops, apertures. Somebody asked about patch antenna. Patch antenna arrays are very popular. So it could be different type of structures. And just to comment, so any structure, all structures which are carrying current, if they're carrying current, and if they have any sort of deformity, it will radiate. And the radiation will depend upon how the deformity has formed, but it will definitely radiate. So everything can be an antenna at different frequency under certain circumstances. But antenna engineering is when you uh, want to have a wave, when you want a wave to propagate at a certain frequency at a certain conditions, is the engineering about it. So how do you change the deformity to help you in your engineering problem? So also there are structures known as reflectors or lenses, which are used to then manipulate these waves. We won't be getting into these, but it's a very interesting area. Materials, meta lenses and stuff are there, which modify how the waves propagate in space. Among radiation characteristics, so these are the topics which we'll see in the next class. Field pattern, directivity, impedance. So these bandwidth, these are the properties around which we try to model our antenna. So you might need a certain sort of pattern. You might want it isotropic, omnidirectional, or you might want it to be in just in one direction, with a narrower beam width. You might want two beams. So that is how what the field pattern would be. If you don't follow, don't worry. In the next class, we'll discuss them in a greater detail. Directivity is how much, the amount of gain you want in one direction, how narrower the beam would be. Now the impedance is you might have a circuit, and from that you want to radiate. You might want to launch a wave, and so you will have to match the impedance of the circuit to the antenna so that the wave radiates. And then the bandwidth, you might want a narrower bandwidth for some bands. Some bands are wide. Some bands are wider. So these are different properties that you want you engineer your antenna around. Uh, yeah, again, the so these properties will be studied in this course. So to start with the electromagnetic radiation, we must remember the Maxwell's equations, and so which relate the electric and magnetic fields in time. And we so in electromagnetic theory, we saw the Maxwell's equation where there were no sources, or they might have been sources. So in over here, we will have sources in them. Rho and J are the terms which are basically sources, so they will be here. But there are some difficulties around modeling antenna structures because the current distribution on them is not very simple. So you have to do a lot of approximations and but all things considered, we generally get a very good model of how the antenna would work. So if you consider a geometrically simple case of a straight conducting wire, so uh, let me switch to a pen. So a straight conducting wire is a linear antenna. So even for a simpler geometry, which is excited by a voltage source in the middle, even this has been it's still the research is being conducted on how it radiates, and the exact charge and current distributions on the wire. Okay, so when we usually do maths, the wires are usually simplified a lot. The thickness is the cross section is reduced. We assume a lot of current flowing on surface and stuff. So which is not ideal, but it gives us a fair idea. So we consider finite radius, and so all these things are considered. But radiation fields are not very much affected by these things, so approximations works in our favor. There might be slight deviations, but we can explain them, and for practical purposes, we are able to make good models for these antennas. Okay, so by combining the Maxwell's equations, we can derive non-homogeneous wave equations in E and H. So a lot of words. Essentially, we're saying that we need the Maxwell's equations over here. Um, so let's. I'm assuming everybody remembers the Maxwell's equations, and so and from there and in electromagnetic theory we had discussed we had this what do we call them? The auxiliary potentials, the auxiliary vector potential and the auxiliary scalar potential. Just give me a second. Okay, sorry about that. So in electromagnetic theory, we had discussed about scalar and vector potentials. So we can find the magnetic field and the electric field using these two. Okay, and this is and if and for simple harmonic time variation, that is we are replacing this d by dt by g omega. We will get these set of equations. So I hope this is clear. Okay. Um, so we'll start with the auxiliary potential functions, and to yeah. So basically, what we do is we try to find out the auxiliary potentials, and once we have these auxiliary potentials, we can find out the radiated electric and magnetic fields using these. So just to remember, we have the Maxwell's equations. And from the Maxwell's equations, we have the auxiliary potentials and the from auxiliary potentials, which can be calculated from the sources. So we'll see the formulas for auxiliary potentials, which will have rho and current, and these stuff from. So and okay, so from Maxwell's equation, we derive the auxiliary potential, and from there we have, we define the auxiliary potentials, and which can be found out using charges and currents. And once we find out the auxiliary potentials, and we can use them back to find out E and H, which are the electric and magnetic fields, which is our goal. Okay, so this will come again and again in this class. So we find out we have to find out A and V, which are calculated, uh, from uh, current and charges, and which can, from using A and V, we find out E and H. And there could be different ways of going about this. You can find out, using these, you can find out the magnetic field, and then you can find out the electric field, or you can find them separately also. Okay, so these the potential functions A and V are themselves solutions of non-homogeneous wave equations. So uh, if you go to the chapter 7 of DK Cheng, you can go through, you can look at how these equations were formed. But essentially, if you look closely, both these equations look like wave equations, non-homogeneous wave equations, because we have some terms over here. If these were zero, it would be homogeneous. Um, so the both of them look very similar, and they are known as non-homogeneous wave equations, and their solutions look like this. V and A. So for this particular equation, the solution looks like this, and this particular equation solution looks like this. So they themselves are solutions to non-homogeneous wave equations, and yeah, for harmonic time dependence, the phasor retarded potentials are so. Yeah. Okay. So you see this term over here? So this is basically retarded potential. That is, there is a delay. Uh, so if you have an antenna which is radiating over here, okay. So so wave is radiated at P naught time, and there is a position where you want to measure the electric field and magnetic field. So this particular wave which was launched over here at T naught will reach over here at some T1. So this time which uh, like the time delay is uh, called the retarded potential, and this could be calculated. For example, if this is at a distance r, and the wave is propagating at velocity v, so the time speed is equals to distance by time. So the speed over here is v, distance over here is r, and time is t, and so the t would be equal to r by v. So that's what this r by v or r by u is over here. So this basically says the retarded potential, and then this could be written like this as well in the Euler notation. Okay, so we have the auxiliary vector and scalar potentials. The solutions look like this, where there is the term for retarded potential in both of them, and again this could be written like this over here. Now over here, k is the wave number, which is defined as 2 pi by lambda. So going through these things which are very closely related to electromagnetic theory. So if you revise this course, you will be able to recall all of this. Now, A and B are related by the Lorentz condition for potentials, and just as J and P are related by the equations for continuity. So if you remember, this is the equation for continuity. Just recalling, this is how it looks like in time domain, and this is for the harmonic uh, time, where we replace d by dt by j omega. So this is kind of recalling all the equations that we have already seen in electromagnetic theory, and uh, the idea over here is that instead of solving for electric and magnetic field from rho and j, we introduce a and v to simplify our problem. So you can see both a and v themselves are solutions to wave equations. So we somehow inherently solve for e and h, and we just have to do some dot or cross products to get our answer. Okay, so again, so to simplify our needs, we don't have to evaluate. There's no need to evaluate the integrals in both equations 11, 3, and 4. So for a and v, both of them are given as the integrals. But what we can do is we just have to evaluate for a over here, and then we can use that information to find out e and h. So, as a matter of fact, E and H are related like this. E is equals to some constant times del cross H. So if you have H, you can find out V. Now we need to find out H. So these are the steps. We determine auxiliary vector potential A from J from 11 3. So this equation is what we'll solve first. We know the current distribution. So this information will be known to us. J is the current distribution. So we know J, we find out A by integration. Now from A, we can, once we have A, we can find out H. So from A, we can find out H. And now once we have H, we can find out E. Okay. So from H, we can find out E using this expression over here. So do we have the idea? I think so. So I'll pause over here because I covered quite a few slides. So if you have any questions, you can ask them by unmuting yourself or write in the chat. Um, Also, if you were not able to follow anything, I'll recommend going through I think chapter 7 of DK Cheng. So this is on wave propagation, I think, this chapter.
Sir, do you have that book PDF?
Yes, I do have it. Do you want me to share it? I can do that. If you
Yeah,
need it
please.
immediately, I'll pause the class and send it in the WhatsApp group. Or if you can wait for the class to end, I will share it after the class.
Yeah, sure. Thanks.
Okay.
Just
Okay.
to
So,
I'll share. Yeah, I'll share the book at the end of the class. So basic, it's a very good book. Go through the electromagnetic theory, just brush over it, and then you'll be able to follow the equations which are there in chapter 11. There's a question: are we going to solve any numericals? I think we'll solve a few numericals, but they will be more towards the derivation of equations because uh, that's will what we intend. Okay, somebody there's a yeah. So there will be some numericals, maybe not in the terms of finding how much the values of fields, but what would be the expression, that sort of numericals. How do you find J? So J is already known. The distribution is known. So, for example, if you have a current dipole with a current, you define how the J would look like. Does it look like this, or does it look like this? So when I draw this, you might not get an idea, but usually we define J as something as some expression of, for example, sine or something function. So this is, you define the J. If you have a structure, for example, if you understand patch antenna, so this is how it looks like, right? So you know how the current is flowing on this. If you give an excitation over here, and then you know how the current would go about this. So J is known, is what I'm trying to say. And any other questions? So book I'll share. Numericals will do some. J is known. And will there be any design case studies planned to discuss? If by design you mean dipole antennas, yes. Array factors, yes. Um, HFSS CST, no. We won't be using any EM solvers. As an extension of this course, maybe in future I can plan a course around MATLAB sometime, but in this particular course, we won't be doing it. So there's another question. MIMO arrays. MIMO, no. Arrays, yes. So array is yeah. So array factor and stuff, I think will be doing it, but later in the course. If you want a more detail, so I just remember so if you want to go through a more detailed course, there is a course on NPTEL. I hope I'm writing it correct. NPTEL by Professor Girish Kumar.
Yes, sir. One course is there, antenna by Girish Kumar and I
Yes.
think Dr. Bhattacharya from
Okay.
IIT
Yeah. Okay. So I've not been through the course by Professor Bhattacharya. I've done the course from Professor Girish Kumar. It's an excellent course. If you want to go in more detail or a more slower paced course and with some good jokes or bad jokes if you like them, like whatever. But yeah, so he teaches very nicely. If you want, if you can also do that course as well. So the lectures are already there on NPTEL, so you won't have to wait for me. Another question, is it only theory or some basic design using ADS Virtuoso? So I'll repeat again, there will no tools would be used for this course. This is a theory course. We'll derive expressions, we'll understand how things work. We won't design them. There's okay. The NPTEL course link. Just search for antenna theory by Girish Kumar. I wrote the keywords over here. NPTEL Girish. Just write this. You'll get. It's from IIT Bombay. Okay. And I think he has done some examples in ADS. I think, or is it for a different course? I can't recall. Will be doing beam steering and all those using array? No, no. Will design the arrays, how they have to be spaced, how the beam would be if that is the case. Somebody pasted a link. I think it's for the NPTEL course. You can refer to that as well. So there are good courses out there, and this is also a course. And most courses cover Balanis or they are curated. I'm referring to DK Cheng for but the slides. Okay. Any more questions? So in the next slides, the next few slides will cover electric dipole and magnetic dipole, and then we'll end the class. So a few more slides to go. Like we are at 16, we'll be there up till 30. Okay. So you have to note that only step 1 over here requires an integration. So finding A from J, which is over here, will require an integration. Once you have done this integration, and then this is a fairly simple integration because J would be some combination of sine, cos, all those functions. So and integrating sine, cos. So don't worry about this dv. When with this, you'll change the coordinates, and this will become to something like dr d theta d phi uh, if it is something in spherical coordinate system, or if you have a dipole like this, you could just go to dr d theta in the cylindrical or something like that. Maybe I'm writing it wrong, but uh, this is a volumetric and integration. So you can change your coordinate system to fit your geometry uh, on the basis of the current which is flowing. So if you change the coordinate, so you just have to know which coordinate system to move to. So, and by symmetry, you can probably guess. So if you just switch the coordinate system, you'll be able to do the integration fairly easily. Um, and the integration will probably be based on what you have studied in like CBSE class 12 integrations. Those sort of stuff would be there. So I don't think it will be any complex unless you make a very complex system. So you probably have to revise this to solve these integrations. Once you have done this integration, all you need to do is do a cross product here and do a cross product here. That's it. Then you get your magnetic field and the electric field. So fairly straightforward. And this is what something will be used to find the radiation pattern of antennas. So over there, what you will have, you will have an antenna, some structure antenna, and you'll be given the value of J, like the expression for J, and then you will be asked to find out how the radiation pattern looks like. So if you solve the electric, if you solve E, and you'll be able to plot the how the pattern looks like. Okay, so that's it from the introduction, like some revision of what we have done in electromagnetic theory. We'll start with the radiation fields of elemental dipoles. By elemental, we have electric dipoles and magnetic dipoles. Also, there's something called as duality. So we'll discuss everything for electric dipoles, and then we'll show duality. Similarly, we can do it for magnetic dipoles as well. Okay, so you have to consider this where we have a small wire which connects two disks, and they have plus Q and minus Q charges on them, and then there's this wire which connects them. Uh, uh, okay, so this is how they set up. So since these two are opposite charges, there will be some current flowing through this wire, and then we are trying to find out what will be the electric and magnetic fields over here. Okay, so this is how the setup looks like, and this particular thing is known as an oscillating electric dipole, because we have two charges and there is a small current over here. So this current flows through this direction. Yeah, so there are oscillating charges. So this is an elemental electric dipole. This is the setup, and the point is r distance away, and this particular length is dl. So remember that this length is dl. This we have current as I flowing through it, uh, and the field where we're trying to find out is r distance away. Okay, so we are starting as engineers. We do assumptions. We're starting with the assumption that the current in the wire is uniform. So again, somebody had asked, how do you get J? So see that this is how we define J. We assume that there's a constant current flowing. So J becomes a constant. So this is how the uh, sorry, not constant, but like this uniform current, that is the magnitude remains the same throughout, and then it is oscillating. So we have a cos omega t term over here. So the field is sometimes like this, sometimes like this, and it keeps oscillating. Okay, so this is okay. I made a mess. Maybe yeah. So this is how the current looks like. So we have the expression for current now. The current vanishes at the ends, and so the charges are deposited over here. So this we're just discussing how the source is made up. Now the relationship between the charge and the current is given over here. So this is known to us. dq by dt is it, and we know how the current looks like. Because we have defined how the current looks like. We assume that the current is flowing like, and the current has an expression like this. Again, phasor notation, you can write it like this, where we replace d by dt by e power j omega, like, yeah, this term. So if you take the real part, this j omega will come out, right? So basically, we are writing it in different forms now. We don't have to care so much about it. The important thing is we defined the setup, we defined the current, which means we have defined J. Okay, so current looks like this, or charge looks like this. Oh, okay, so we have the expressions for current or the charge now. Now we have the current distribution or the charge distribution. Um, okay, so now we can define the dipole moment. So the electric dipole moment has an expression like this. So this comes again from the uh, electric field, or like the first chapter or second chapter, uh, electrostatics essentially. So this is how the electric dipole moment is defined, which is P is given as Q into dl. So this is we have the value of charges, we have the distance between those charges. So Q into dl gives you the phasor electric moment. So essentially, the electric moment don't care about this. So we have got the electric moment now. So this and hence this particular setup is known as, and this particular setup is something what is called as a Hertzian dipole because of Hertz. Okay, so we have defined the dipole now. We know the charge distribution, we know the current distribution, we know the dipole moment now. Now what we do is we do these steps again. So we have to determine A from J. J can be determined from I. Once we have A, we will calculate H, and once we have H, we will calculate E. So let's do that. Okay, so I've written the expressions for A and V over here, and we'll just be needing, I think, the A part. So over here, yeah, the phasor notation for retarded vector potential from equation 11.3 is given by this. So this is the expression for A. Now J uh, will yeah, so you can, instead of writing J, what we have done is we have removed the integration and we have written ideal over here. So if you integrate and stuff, you'll get this expression. So essentially these are same. Okay, so A is given by this expression. If you are stuck, maybe revise. Okay, my pointer is creating some issues. Okay, so yeah, maybe if you feel problems with this expression, revising EMT is maybe a good idea, or you can refer to text as well. So once you have got, we have defined, we've got the expression for auxiliary vector potential over here, uh, where B is 2 pi by lambda, and okay, so now we what we do is we'll shift coordinate systems. So over here, right, what we were looking at was, like, for example, an XYZ coordinate, but over here, due to symmetry, a cylindrical coordinate system would be better suited to solve the math problem. So this is just to make your math, like your like solving the math more conveniently, which will shift to a cylindrical coordinate system. So AZ is now defined as AR cos theta and A theta sine theta. Okay. Okay. There's no questions, right? Okay. The spherical components of A then are given by this expression over here. AR. So A is a small a. Theta. AR, A theta, and phi are the basically the directions. Uh, Okay, so not cylindrical. My apologies. So this we are using spherical coordinate systems. Okay, now we're okay. So basically, solving this in Cartesian coordinate will be difficult. We're shifting the coordinate systems. This is a spherical coordinate system, and and over here, what we have is the expression for A in the Cartesian coordinate. So what we did was we gave the expression for, because over here this was in Z direction, right? So in Z, your vector potential could be easily defined in the Cartesian coordinate system in the Z direction. So we defined it in the Cartesian coordinate, and now but you have to find out electric and magnetic field, and calculating them would be much easier if we shift to a spherical coordinate system. So what we do is we have got the expression for vector potential in Cartesian. We'll shift that to the spherical coordinate. So for doing that, we just have to refer to the textbook of how, like, to change this. Okay. So my pointer is there's some lag with this, and it's breaking. I just want to check if I'm audible, and can you see my screen?
Yes, sir.
Yes, sir, you are audible, sir.
Okay.
Everything is fine.
That's everything is fine, right? Okay. Because the pointer was lagging. Okay. So up till now, what we have done is we defined the Hudson dipole. We got the currents and charges. We defined the dipole moment. We have the current distribution with us. We defined the auxiliary vector potential. The actual auxiliary vector potential was defined in the Cartesian system because it was easier to define in the Cartesian coordinates, but we need to find out electric and magnetic field, which will be easier in spherical coordinates. So we are now modifying the Cartesian coordinate system, like we're modifying the auxiliary potential uh, from Cartesian to spherical. And by using the conversion table, which you might find on the internet or in textbooks, you can easily write AR, which is the radial direction in the spherical coordinate, as AZ cos theta, A theta is minus AZ sine theta, and A phi is 0. Uh, okay, so we have got these expressions over here. So A phi is 0 because the expression will involve terms only from x and y, and hence this becomes 0. So up till now we have found out the auxiliary vector potential in the spherical coordinate system. Now the next step would be finding out uh, the magnetic field. So I'll shift to a pen. Okay. So we defined I, and then we defined A, and now we have to do H. So this was in X, Y, Z, and then we move to R, theta, phi. We move to R theta phi. Now we'll just put the value of A over here and take the cross product over here. So again, um, just the math is tedious because you have to do a cross product now in spherical coordinate system. So this is how it looks like. You put the values of uh, the way the Cartesian, yeah. So you put the auxiliary potential values like this, and then I think if I remember correctly, what you do is you do something like this and multiply with this term. So if you remember taking a cross product, right? So you have to do that. And now since A phi is 0, this particular term is 0 over here. So you'll just you'll end up getting something like this. So you do the cross product, you will get your magnetic field expression as shown over here. The A phi terms, everything would be A phi. Yeah, because yeah, something you do it. Essentially, this term would be 0. This is already 0. If you do cross like this, this will be term, and everything would just come in the A5 direction. So now you've got your magnetic field, and once you've got the magnetic field, the next step is to find out the electric field. Take a cross product again with H, take its curl. So yeah, and if you take a curl, this would end up something like this. Yeah, so this essentially tedious mathematics is involved, but you get the idea, right? So you define the current, then you find out A, and then you find out H, and then you find out E. So upon doing that, if you do the math correctly, your expressions will match these. So you will get an ER, E theta, and no E phi, and H will only be in phi direction. Okay. And there'll be some term which there you will end up with a ratio which looks like root over mu naught on epsilon naught, which is defined as eta naught, or the intrinsic impedance of free space, which which whose value would be 120 pi, which is I think three. Okay. I'm again the cursor is moving a bit. Are at 50 ohms, right? You design your circuit at 50 ohms, but you want your waves to propagate in space, but the space is actually 377 ohms. So essentially, antenna is an impedance matching circuit. Like, don't take it very literally, but antenna is essentially impedance matching circuit for 50 ohms to 377 ohms. If you match if you match the impedance properly at that particular frequency, the antenna uh, will radiate your wave which was on your circuit into the free space. Now again, the engineering problem becomes difficult if you want to launch a wider range of frequencies. Matching them at one frequency is fine, but if you want more frequency, so that's what an antenna problem is. You're matching your circuit to free space. Okay. So equations 15 and 16 over here, like this is entirely 16, are the dipole. So we did it. We have calculated electric and magnetic field for a Hertzian dipole. And if you have noted that we only had to find out the vector potential A, and we did not find out V. Okay, we did not have to find out V. So we can also calculate uh, by using V. What we would do is we'll calculate A and V, and from A and V we can calculate E instead of using this expression, and H will be calculated from A. Did you follow? So yeah, what we can do is we can find out A, and we can find out H from that, and to find out E, we will uh, use A and V, find them out, and then put them over here, and we can get the value of E. So you can go through this method as well, and you'll get the same answer. But maybe a good idea would be try doing that, because we have already done uh, mm, using this expression. You can try using this expression. So before we start the near field and far field for uh, electric dipole, I'll pause over here and take questions. Or you can just look at the slide, and we'll pause over here because taking breaks are important. So there's a question: 377 ohms is space impedance. Is it constant? So for free space, yes. Is it constant throughout the universe? I think so, unless there is moisture, humidity, and other factors. It might be different for dry air as compared to humid air, but for free space, yes, it is 377 constant.
Sir, that free space, how to match for the wideband feed, sir, ultra wideband feed and all. Actually, I am an antenna designer working on antenna design, so which works from some 200 to 2 gigahertz, 200 megahertz to 2 gigahertz kind of a thing. So how to match this impedance for 50 ohm at the output and open to space that 377 ohm. Do you have any techniques, sir?
Okay, maybe what you can look at, you can look at antennas. You might already know Vivaldi antennas and horn antennas. They are they are designed to match for a wider range. Uh, like you have a coax as your feed, which is usually 50 ohm, and then it matches throughout the for all the frequencies. I think I've seen horn antennas in that frequency range. Okay. So horn antennas look something like this. So tapering is one of the methods which is used for wideband matching. If you will see them on microstrip as well, or in antennas as well. So what I usually like try to visualize is this aperture is essentially helps the wave which is propagating to launch into the free space, and this aperture decides the frequency at which it is launched. Question: can we use Smith chart for this? I think you can, but I have I have not used Smith chart as much. But yeah, you can definitely use Smith chart and for this. I'm not sure how. Please don't ask me how, because I'm not. I have done matching and stuff for circuits, filters, and stuff. But antennas, I'm not sure. But yeah, so Hanumant, is it? Yeah. So you can look into Vivaldi antennas and horn antennas. Maybe you can get an idea of broadband matching. Uh, if you are not concerned about the size of the antenna, if that is a concern, then you'll have to look into more papers on that.
Mm-hmm. Actually, sir, there are two compromising values here. One is the return loss performance, where the tuning is happening from 0.2 to 2 gigahertz. That is fine. But when it comes to the radiation pattern, then I'm not satisfied with that. So, sometimes in some Vivaldi designs, I'm happy with the radiation pattern, but not with the return loss performance. So I have to compromise both of them together. So that's where I'm looking into.
I'm
Yeah.
pretty sure you know more about this topic than me, because you are asking very good questions, and I get idea. Like I don't have an answer to this, uh, but you can go through more literature. That's what I can say, because you know what you are trying to optimize and you know the problems better.
Okay, fine. Thank you.
There is some comment. Don't need match to antenna. From impedance to free space impedance matching, that's available path loss. I'm sorry, I could not follow. Maybe this was meant for you, Hanumant. I'm not sure whether it was meant for the class or something I said. Purushottam, maybe you can rephrase the statement. Okay. There's another question. How about log periodic antenna wideband? Yeah, I think I've seen wideband log periodic antenna, but I'm not very sure about that. Maybe in this course we might go through log periodic antennas, but I think gain will be a problem in that. Uh, and the radiation pattern also is not as good as horn antennas, I think. But okay, but you'll have to compare. So there are antennas, different kind of antennas. So these questions are more based on very specific application what you need. So we are kind of digressing from the course because we will look at the theory on how antennas work, which is more sort of a generalized approach and towards the electric and magnetic dipoles. So very good questions. I can encourage discussions on these on the WhatsApp group. So there might be people working on the same areas. You can discuss amongst yourself as well, share literature, share papers. So maybe that would be a good place to do that. Yeah, you can ask in the class also to me, but since I don't very much specialize on antennas, I'm more of a computational methods guy. But I can try answering your questions. I can look for the internet for you, but if you look on the internet yourself, you might feel that would be faster. Okay, Hanuman, I'm sorry I could not answer your question very like in the matter you might have needed. You can look on the internet, ask in the group, and so Mohan is giving some suggestions. Maybe you can look into that. Okay.
Okay, sir. Thank
So
you.
we'll go back to the course. Okay. So we'll go back to the course because we also want to wrap this class as soon as we can. It's been very long already. So we'll discuss near field and far field very quickly. Okay. So as the name says, so if you have an antenna over here, and so what we can do is we can draw boundary based on certain conditions and call the near field as near field and the far field as far field. Very literal. So near field is near to the antenna, far field is far to the antenna. How do we define this near and far term? Is basically this expression over here. So if you have your beta r, which is uh, which is equal to 2 pi r by lambda, which is this is less than 1. Under this condition, your expressions would change something like this. So this is how it will look like. So this was your magnetic field, right? So this is your magnetic field, which looks like this. And in the near field, this particular term will have a higher effect as compared to this term over here. So what you can do is ignore the first term, just consider the second term, and the e power term can be approximated using this expression over here. And if you solve this, you will end up with H5 relation shown over here, this 1117. So this is how the magnetic field would look like in your near field. And similarly, and this is something similar to what you get if you calculate the magnetic field using the Biot-Savart's law. So if you remember over there also we had a magnetic monopole and we tried to find out a magnetic field at like a particular position around the magnetic dipole or the current carrying wire. So these expressions would look similar. This is just an observation. Uh, do not care so much about this, but this is how the magnetic field looks like in the near zone. Similarly, for the electric field in the near zone, the higher order terms would play a much more prominent effect. Not the second term, just the third term. Just this term and this term will have a higher effect for the electric field. We have defined the magnetic field and electric field in the near zone, and this would again something from a electric dipole. So if you have an electric dipole, try to find out the electric field at certain distance. The values which you get for electric field over here matches to the one you get from an electric dipole. So 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 near field zones of an oscillating time varying dipole uh, are very similar to a static field of a electric dipole with so hence we call them quasi-static fields because they resemble to what you would obtain from electrostatics. So you get this expression over here, 331 is obtained from electrostats, and the expressions over here, this is obtained from uh, like electromagnetic theory. So over here you have time varying fields, over you have static electric fields, but the expressions look similar. So the near field zone is known as the known to have quasi-static fields. So they resemble static electric fields. Okay. And then about the far field. Okay, so in the far field, just this because the relationship becomes greater than one, and then what will happen is now these terms won't matter. So you can just ignore the higher order terms, and you'll end up with an expression for electric and magnetic field. So this is how the electric and magnetic fields look like. And if you look them closely, they if we look at them closely, we can make some observations. For example, we have the magnetic field and electric field in orthogonal directions. So they are in space quadrature, but the phase term is the same. So they are in same time phase. So they are in the same phase, but in different space quadrature. So they are at an angle, is what we can observe. If you take the ratio, it will come out to constant, which is equal to intrinsic impedance of the medium. And in this case, this is free space. Okay, so this is the second observation, and the also if you if you look at these equations, the electric field and magnetic field equations resemble to those of a plane wave. Here and you have a distance where before which you call as the near field and the far field. So what happens is in the far field, the waves appear to be plane waves, and so this is not unexpected because at a very large distance, if you have, for example, if you have a small source over here and fields are being generated at very large distance, this the wavefront would become like uh, will look appear like plane waves because if you keep increasing the diameter of a circle, at some point it would like a plane. So if you make this infinite, this will become exactly plane. uh, okay, maybe you guys can follow. A very stupid example would be the earth. For us it appears to be plane, but it is actually spherical. But so a very bad analogy, but that's what we're trying to convey. In the far field, the spherical wavefronts resemble a plane wavefront. So in the far field, hence some of you might know that when we do experiments using antennas, we'll keep the objects or the antennas in the far field. When we say far field, and we, for example, 2 meters, 3 meters, or something, we calculate the distance known as the far field, and we keep antennas at that place because if you're trying to illuminate an object, we make sure that we are doing with plane waves. Some of you might be working with meta surfaces, and when you do measurements, you try to keep the antenna in the far field so that the meta surface is illuminated with plane waves. Okay, so and the third observation, okay, after this, we'll take a break and take questions. The third observation is that the magnitude of these waves in the far field zone varies inversely with the distance of the source, which is like very obviously. So the strength of the electric and magnetic fields become lower as you move away from the source, from your dipole antenna in this case. And the field, electric and magnetic field, th- they're a periodic function of r with the period, that is wavelength. This, so yeah, over here, this term over here. So the field strength, it is a function of r, and r uh, with a period which is this 2 pi by lambda. So there is a beta term over here, which will yeah base yeah. So this product defines the periodicity. So essentially, if you have a source over here, your electric field magnitude will become greater, lesser, something like this. The magnitude strength would be at very far distance, the field will diminish, and at very even at close, even if you are closer to antenna, there might be nulls at some places. Yeah. So no, note that the far zone condition translates into beta much greater than translates to r greater than lambda upon 2 pi, hence one has to be farther away from the dipole at lower frequencies. Okay, so this is an observation that for lower frequencies, to be in the far field zone, you'll have to be at at a greater distance, because this particular r, which is the distance uh, 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 where you are looking for at the wave, uh, uh, should be greater than lambda upon 2 pi, and for lower frequencies this lambda is greater. So hence you have to be farther away to experience a plane wave if you are at a lower frequencies, if you are at a lower frequency. Okay, so we'll pause again over here, take questions. We have 4 or 5 more slides to go. Any questions from near field, far field, and what we went through over here, the expressions for E and H. So if we
Sir
recall, we
Hanuman here.
started. Yes, yes, Hanuman.
Sir, if you have a feed which is the parabolic dish, so will that parabolic dish will change the phase of the waves coming in?
Parabolic dish will what we are expecting from the parabolic dish? Change the field.
Will that change the polarization? For example, from horizontal polarization is we are transmitting. So once we receive at the end, it will be like a vertical polarization or the same horizontal polarization. If we use the parabolic dish as a reflector.
I yes, Purushottam, please answer.
It depending on the horn.
I'm sorry, I could not follow. Can you repeat the answer or write it in the chat?
It depending upon the horn, sir. Horn.
Depends upon the horn. Hanuman, were you able to follow? He's saying it depends upon the antenna, which is radiating, I think. Uh, so if, as far as I know, the polarization it depends upon the source, but you can obviously modify using different structures. For example, a parabolic deflector is sort of a lensing effect you might get, but I'm not sure whether it can change the polarization. But I'll have to look it up. Maybe I'll write this in the chat so that I can look it up and maybe answer your question in WhatsApp. You can also search for it.
Okay.
Uh, 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 I have written the question. Uh, what you intended to ask, is it correct? If you can also modify the question and write it in the chat so that I can look it up. Purushottam has an answer which says it depends upon the feed of the horn. I'm still not able to follow way, because I don't have any expertise on this. But okay. So there's another question from Ramesh. Where did we derive 2 pi r by lambda? Um, okay, so this particular term comes from, let me go back from the, if I remember correctly, from this particular part. Yeah, from the exponential, if we, yeah, just give me a second. Even I lost my train of thoughts. Um, yeah, it has something to do with the exponential terms over here. So this is something which we expand, so we get something like this. And this particular, yeah, so this particular term over here, right? So this, yeah, yeah, this term somehow, this has to be okay. Yeah, I think I follow. Um, so to judge the nature of this exponential, I'm still like I have to look it up. If I'm wrong, I'll give you a correct answer in the next class. But if I remember correctly, to judge the nature of this exponential, we take a point where, yeah, something, it has to do with the fractional value. So at some yeah, so this beta r has to be less than 1. Yeah, it should be from this only. From we take this particular term, and if it is um, less than 1 or okay, I'm actually stuck. I don't want to give you an ambiguous answer. I'll come back to you. But it has something to do with either the fraction or the exponential value, and based upon this, the nature of the field would either be decaying or propagating. So actually the expression what this means. I'll get back to you, Ramesh. I'm very sorry, could not answer your question. This is actually very embarrassing. That should have I should be able to. Okay, so essentially, this beta R, I think it has to do something to do with this, and its nature determines how we approximate. I'm sorry if I don't have a very good answer right now. If somebody in the class knows this, please answer it. I think what I can do is I can just quickly search this on the net. I'll tell everybody else can look up, like look at the slides and ask their own questions. Okay. Any other questions? Yes. Uh, Somnath, I am unable to like figure out what. Like, can you speak up again? Closer to the mic. Maybe I can try answering Ramesh's question again. How did we get the beta R term over here? So we do have the this expression, right? E power minus j beta. Maybe if we plot this, e power some term looks like this. E power negative power would be something which is decreasing, and at some point its magnitude will start diminishing. So based on that, we have done this. Yeah, so this particular term says e minus j beta r is greater than 0 is greater than 1, is it? Okay, okay. I don't think I'm doing it right. Okay, I'll get back to you, Ramesh. I'm sorry. Any other question? Else we'll look at the magnetic dipoles, and then we'll end the class. Okay. Sorry, Ramesh. I just it just clicked. So essentially, the term over here, e power minus j beta r, uh, for values greater than this. If this is greater than 1, so this particular value will always be positive, right? So beta r is known to be positive. Now its value could either be greater than 1 or it could be less than 1. Now, if it is greater than 1, what will happen is this exponential if it is less than 1, this exponential will increase rapidly. And less, if it is less than 1, it's nature. Okay. Sorry, if it is less than 1, so we'll have some fractional values over here. Now, e power something in fraction would be actually a greater value. So it yeah, so it would it's the nature of this particular wave will change. Now it in the near field, okay, again I'm stuck with this. I'll try to phrase what I'm trying to say better, but it has it if it is greater than 1 or less than 1, the nature of this exponential will change. Maybe I'll try I'll plot the function and show it to you in the next class. Uh, okay, so this has something to do with this exponential term over here, Ramesh. I think that's a fair enough answer for right now. I'll do better in the next class. Okay. So any further questions? I was speaking the entire duration. I'll just pause over here for 2-3 minutes and we'll then start with elemental magnetic dipoles. Okay, I guess that was enough time to reflect on the observations for the far field. Now, near field and far field. Now we'll quickly do magnetic dipoles, um, and then duality and wrap up. So let's consider a small filamentary loop, which is like this. It has a radius of b, and again we are trying to find the electric and magnetic field at a certain distance, which is r. But in this case, since the current is flowing in a loop and this position keeps changing. So this is r1 from r1 is the distance from the point where we are considering. So again, we'll have to approximate these distances as well. And we are taking a small uh, dl dash section on the loop. We'll start with the Cartesian coordinate and then we'll move to the Cartesian or the cylindrical coordinate, and then we'll move towards the spherical coordinates. Okay, so we have a current I flowing through the flowing through this small loop, and this will form a magnetic dipole. So we have already seen similar things in the Biot Savart's law. So we'll do that quickly again. So the magnetic moment is given as I r I pi b square. So which is I pi r square. So um, b is the radius and I is the current through the loop. So this is the magnetic moment given over here. And to determine the electromagnetic field, we first find the vector potential as we did. So now uh, uh, this is basically equivalent to your J and I. And now to find we're finding the this vector potential. A is given as mu naught pi mu naught I by 4 pi integral of e power j beta r1. Notice we have r1 over here. Now this r1 is actually changing for all points on this loop. So we'll approximate r1 such a way. So we assume that this particular uh, loop is very small and this b is very small. So this r minus r1 term. So this r over here uh, can be given as j beta r minus j beta r minus r1. So we added and subtracted r over here, and and now this particular term is now constant because this r is from the center of the loop, and this exponential over here can be approximated in this form: 1 minus j beta r minus r1 minus r. So this is the approximated value for this term over here. Okay, so we have approximated this exponential term. Now we have the expression for the vector potential. We have the approximation. We put the approximation inside the vector potential. So this is what it ends up. So the constant terms are taken now, and we are left with this integral and this integral. This integral is actually 0. This di will become something as sin theta minus cos theta or cos a from 0 cos theta sin theta multiply d theta and stuff. So you recall the area under field for sinusoidal functions uh, this particular function, this particular integral becomes 0. And now the first integral, uh, it was already done in the textbook in chapter 6, which is again an electromagnetic theory chapter. Over there, uh, if you have a vector potential looking like this, the solution looks like this. So if you want to see the math, as I said, I won't be doing the math for you. You have to do it yourself. You can refer to the textbook. We got from this integral to this integral. But since we know that solution for this looks like something like this, we only are missing this term over here. So this term can be included, and once that is done, this you get the vector potential over here. So for the magnetic dipole, we have calculated the vector potential. So the steps over here, we define the magnetic moment. From the magnetic moment, we define the uh, auxiliary vector potential, which had current distribution, IDL, and the problem over here was the term R1. For R1, we did approximations, and now once we did the approximations, we got the final value of A. Okay, and we skipped some maths over here, which can be practiced. So the math is essentially if you have that you have to integrate or differentiate, so there is no information or physics involved. The physics involved is how you what structure did you have, how was the current distribution, how did you go about solving the problem. So what we did is we defined the vector potential, we did the math and got the expression for it. Now once you got the vector potential, um, the next steps is to find out electric and magnetic field. So the magnetic field can found out just by taking the cross product. So if you take the cross product, the expression would look something like this. And if you take the cross product of the magnetic field, the electric field would look something like this. So you just have to again take find out the divergence for at these two places over here, and you'll end up with expressions. Now, if you recall, these expressions look very similar to what we did for the electric dipole as well. Okay, so putting them side by side, these are the expressions for the magnetic dipole over here, and these are the expressions for the electric dipole over here. So you can see how they look very similar. Uh, if you for the time being, ignore the coefficients over here. The coefficients might look a little different, but the see the distribution over here. The distributions are same. Now, if you define the electric and magnetic field for electric dipole and magnetic dipole using E and He, we can write these following expressions. E is equals to N naught Hm, where this eta naught. This eta naught is again the impedance of the media or free space. And again over here also we can find magnetic field for electric dipole, which is related to the electric field of magnetic dipole. And to write these expressions, in these expressions, these two terms, the source terms are also related. IDL, which is the source for an electric dipole, is related to the source for the magnetic dipole, which is beta m, where beta is this expression. So they are the duals of each other. So when and we have established that they follow similar nature, and you if we had the expression for the EE and HE, we can easily calculate HM and EM if we substitute uh, these expressions over there. Okay, so if you have, so the other, so right now what we did was we solved for electric and magnetic field for electric dipole, and similarly for magnetic dipole. Now what you can also do is find out E and H for one of them and just use these expressions over here. Divide, multiply them with eta uh, eta naught, and replace IDL with J beta, and you're good to go. You'll get the expressions. Okay, so these expressions 1127 and 1128, these are the results expected from the principle of duality. You understand if you two expressions follow similar nature, and then you can use the one to guess the other. Um, Okay, so the Hertzian dipole and the elemental magnetic dipole are dual devices. Again, because they are the expressions show that they are duals of each other, and their electromagnetic field dual solutions, and uh, their electromagnetic fields are dual solutions of source-free Maxwell's equation. Okay, so okay, so what they're trying to say is the EM fields at the far field, they will resemble the source field Maxwell's equations. So that's what it's trying to. So we don't have to stress about all these things. So essentially, we have we have done we found out the electric and magnetic field for electric dipole, magnetic dipole. We have established the duality. So just for the last like just for the sake of completion, we can look at the electric and magnetic field expressions for the far field for the magnetic dipole in the far field zone. So these expressions are found out using the far field expression for the Hertzian dipole, and then we replaced and the terms I, dl, and those expressions with beta and stuff. So by replacing, we got the expression for the far zone for the magnetic dipole. Again, we can see that far field in the far field, these intensities vary inversely, and they are also the ratio is again equal to beta naught. Next, we'll discuss antenna patterns and antenna parameters. Any questions on this before we close? Okay, so if there are no questions right now, then you can ask them later, or if there are no questions, that's all right. I'll recommend going through the textbook because we did not do math, we just went through the text just to give you an idea, make you feel comfortable while studying. So it's only a few pages from the textbook. You can, if you have doubts from the textbook, you can come back to the class. For Ramesh's question, um, I'll answer you properly in the next class or in the group. Okay. So no further questions. Then we'll end for today. I'll share these slides in the WhatsApp group and upload it on the course website. Recording will be made available soon, as soon as I'm able to upload it on YouTube. I'll say it again. During the duration of the course, you'll need the link to access the YouTube video. Okay, guys, thank you for joining. My apologies for the trouble which happened in joining the class due to the platform. We'll try to resolve that. And thank you for staying with me. Okay. Happy Sunday. See you.